Maths are for me, maths are for you. That. Look how hard me I work, oh God. Now feel maths me work so hard. Confident out there now, one straight A's now. Maths in my world, my world.
Hello everyone, and welcome to Grade 9 Math Online. This is the first in our series of lessons, and I am Nikisha Bailey. Today, we will explore using the distributive property to simplify algebraic expressions using the laws of indices, and also to multiply two binomials. You should already be familiar with the distributive property, as well as with the terms constant, variable, terms, coefficient, expression, multiplier, multiplicand, binomial, indices or powers, like and unlike terms. Here's a quick reminder of the definitions or descriptions of some of these terms. What is a binomial? If you're thinking that bi means two, then you're onto something. A binomial is an expression containing two terms. For example, 2x plus 5 and a minus b. Indices are numbers which tell how many times a term is multiplied by itself. They're also referred to as powers. For example, 2 raised to the third power and y raised to the fifth power, respectively 3 and 5, are called the indices or powers. Like terms are terms that are similar in composition with respect to the variables and the power to which each variable is raised. For example, 3x and negative x have a similar variable and power, so they are like terms. 5a squared bc and negative 3a squared bc are also like terms. So what are unlike terms? Let's find out. Unlike terms, on the other hand, they may look similar, but will not meet all the requirements for them to be described as like terms. Take, for example, 3xy and negative 2x squared y. While they have similar variables, they differ with respect to the powers. In a multiplication sentence, the term or expression to be multiplied is called the multiplicand, while the term or expression with which we multiply is called the multiplier. Having an understanding of these terms will help you to better adjust as we now move into today's lesson. It's time for an activity. Here goes. In how many different ways can you arrange 12 desks in a classroom if they are supposed to form a rectangle? Did you say 6? You are correct. Now make a list of all your options. We have 1 times 12, 2 times 6, 3 times 4. Can you think of the others? Wonderful. 4 times 3, 6 times 2, and 12 times 1. On the right is a pictorial representation of one of these arrangements. Which topics in mathematics can you identify? Very good. Factors, multiplication. Excellent. Now, what is the relationship between the rows and columns and the number of desks? So you'll notice that what is happening here is that you are actually finding the area of a rectangle with dimensions 3 units and 4 units. This concept of finding the area will be used to develop your understanding of how we simplify expressions using the distributive property. Did you know that multiplication can be expressed using brackets? It can. And here is an example. This can actually be read as 3 times 4 plus 6. How do you think we can represent 3 times 4 plus 6? Did you say 3 groups of 4 plus 6? Let's see what that looks like. Now, if we should describe the representation in terms of the respective columns, what would we have? If you said 3 groups of 4s and 3 groups of 6, you are correct. So that is 3 groups of 4 and 3 groups of 6. Let us look at how we would write that. 3 times 4 plus 3 times 6. And this gives 12 plus 18. How is this different from the first representation? We wrote the products separately, and then we wrote the products as a sum. This is what the distributive property allows us to do. Now, we will explore using algebra tiles to model and help us simplify algebraic expressions with the distributive property in mind. So I'll be doing some demonstrations for you today. To participate or practice using the algebra tiles, feel free to go to the link that is now on your screen. There are 3 double-sided tiles available, giving a total of 6 representations. These values are x squared, negative x squared, x, negative x, 1, and negative 1. Now, each of these tiles represent the positive and negative versions, and they're usually distinguished by their color. These values represent the area of the tiles. For example, the x squared tile has dimensions x unit by x unit, while its opposite has dimensions negative x unit by x unit. So generally, the negative versions of the tile have one dimension that is negative. This key identifies the colors that will be used to represent each value during our exploration. Let's start off with 4 times x plus 1. What are the parts of the expression? Very good. I am hearing the mathematics vocabulary being used. 4 is our multiplier and x plus 1 is our multiplicand. The part in the brackets is also known as a binomial because it has 2 terms. Now, what tiles will we need to model this expression? So here we will need the x tile, also called the 1 by x tile, and the 1 by 1 square tile. Putting these tiles together to form a rectangle will give us x plus 1. And based on our knowledge of the meaning of the brackets, we can say that we need 4 of these joint x plus 1 tiles. So here's what the finished product looks like. Where the dimensions of our rectangle are 4 units and x plus 1 units. Now let's take a look at another example. Negative 2 times x plus 5. We are familiar with the multiplier being positive, but here we have a negative multiplier. What does that mean? Now don't be alarmed. It simply means that we want the opposite version. Therefore, if we apply our new knowledge, we'll realize that we need the x tile and 5 of the 1 by 1 square tiles. And the 2 tells us we need 2 sets of these combinations. There we have it. And this represents 2 times x plus 5. However, that negative sign further tells us that we need to use the opposite versions. Therefore, instead of using the positive values, we use the negative. So let's flip. Now let's have a discussion. Based on the examples we just did, suppose we wanted to split the rectangles to show the like terms. What would be the area of the separate parts in each rectangle? Here's a reminder of our rectangles. So while you think, consider these questions. Can you explain how 4 times x plus 1 became 4x plus 4, and how negative 2 times x plus 5 became negative 2x minus 1? Let's take a look at what this looks like. So 4 times groups of x plus 1 gave 4 groups of x's and 4 groups of 1's, and this became 4x plus 4. Now you might be thinking, hey, isn't this the same distributive property that we learned in arithmetic? Well, guess what? It is. We essentially distributed the 4 to get 4 times x and 4 times 1. The 4x came from the 4x tiles, and the positive 4 came from the 4 positive 1 tiles. Also, the negative 2x came from the 2 negative x tiles, and the negative 10 came from the 10 negative 1 tiles. Here's another example. Now, in this case, we will use an algebra tile mat to assist us in arranging the tiles because our multiplier is no longer a numerical value. So this time around, we want to model x times x minus 2. Now, the tiles we need for the multiplier will be an x tile. For the multiplicand, we also need an x tile and 2 negative 1 tiles to account for that minus 2. The aim is to use tiles with similar dimensions to cover the area on the mat. Now take a look at this. Can you tell why a blue x square tile was used? So it was used because we needed a tile that had dimensions x by x. Now for the other area, we need to use a tile that has a length of x and a width of -1. And that is a description of the tile that represents -x. Now don't forget that a negative sign means the opposite of. So we are not expected to use the x tile here. The same would go for the other section of the area. Now our next example is -x times 2x minus 1. Let's see what this modeling would look like. Do you agree? Okay, let's continue. Now, can you tell why a positive x tile was used in this instance? You'll notice that both dimensions included negative signs, which indicate a double flip. Also, -x times -1 gives us a positive x. Now, finally, we'll attempt to model x plus 1 times x minus 2. Now, what do you notice here? We are modeling two binomials. Now, do you think it will be any different from what we were doing before? Let's take a look. Now, here we have an additional row to fill, and this means we have more terms to deal with. Now, notice that we have two negative x tiles and one x tile. When opposite tiles are combined, they form zero pairs. Therefore, if we combine one of the negative x tiles with that one x tile, it would form a zero pair. Therefore, the expression we will have left that represents the area is x squared minus x minus 2. Wasn't that fun? Think about the following questions. What patterns have you identified during our exploration? Also, what conclusions can be made about using the distributive property to simplify algebraic expressions? Let me give you some time to think. Okay, so far we know that algebra tiles can be used to model algebraic expressions, that the distributive property tells us how to expand expressions in the form of A times B plus C, where A can also be a binomial, and basically that each term in the multiplicand is multiplied by each term in the multiplier. Now, in the last example, x plus 1 times x minus 2, what if I had changed the power of x in the multiplier to 2? How would it affect the product? So this is our new expression, x squared plus 1 times x minus 2. Very good. The power of x in the product would become 3. Can you identify which law of indices just came out in our exploration? Here's a quick reminder of the laws of indices. Good. If you selected number 1 from this list, you are indeed correct. So when we multiply terms that have similar variables, we add the powers of the variables to get the power that will be in the product. So multiplying those two expressions, or those two binomials, we see where they both had x's. In the first binomial, the power of x was 2, and in the second binomial, the power of x was 1. So based on the first law of indices, because they both have the same variable x, when we multiply those two variables, we add the powers. So 2 plus 1 gives us 3. What else would change about this new product? If I had changed the power of x in the first binomial to 2, what else would change about our product? So we know that firstly, instead of having x squared as we had in the previous example, this would become x to the third power. Now, what would be the other terms in our expansion? So in our summary just now, we said that basically each term in the multiplier is distributed to the multiplicand. So if we distribute x squared to the multiplicand, we would have gotten x cubed, because x squared times x gives us x cubed. And if we multiply that same x squared times negative 2, we would get negative 2x. Now, if we should also distribute the 1 from our multiplier, it means that we're multiplying 1 times the x in our multiplicand, and that gives us a positive x. And 1 times negative 2 gives us negative 2. So our expression would be, and I hope you're writing this down, our expression would be x cubed minus 2x squared plus x minus 2. Now let's continue. Now that we've looked at a few examples, please use some time to answer the following questions. So simplify the following. Number 1, 5 times c plus 5. Number 2, x squared times x plus 8. Number 3, p times 4 minus 3p. And number 4, r plus 4 times r plus 1. Now let's see how well you did. So these are your solutions. For number 1, 5c plus 25. Number 2, x cubed plus 8x squared. Number 3, 4p minus 3p squared. And for number 4, 4 squared plus 5r plus 4. Now here's my closing task for you. Simplify 3x squared plus 1 times 2x minus 5. If you got 6x cubed minus 15x squared plus 2x minus 5, you are correct. And at this point, we have come to the end of our session. Thanks for tuning in.
Maths are for me, maths are for you. That. Look how hard me I work, oh God. Now feel maths me work so hard. Confident